Hello, this is Professor Cummings. I want to give you an example of doing mathematical models used for the mixing problems or changing systems. The whole purpose of this is not just to go through the differential equations and the solutions of actually, solving the problem, but to more or less show you how to set the problem up from a word problem into a differential equation and then finally come to a solution for the problem. Now, I want you to give you just a rough problem setup. This isn't the problem we're going to work through, but it's just I'm using rough numbers just to give you some ideas what the thought process is, so to help build up that your intuition on it. Remember, the setup of the problem is you've got a tank, and this tank you've got a known volume of fluid, and you've also got a known volume of concentration or a known volume of substance dissolved into that fluid. This is going to be your initial value. This is the condition before the spigots even come on into your system. You also have a concentration, a known concentration, and you got a known flow rate. And you got the flow rate going in, and you got a flow rate going out. Now, this concentration that's going into the tank is actually very important because this lets you know not just how fast you're putting fluid into the tank, but how much of that fluid is the concentration that you're concerned with. So let's say you've got a dye or a sugar or a salt or some chemical that you're trying to enrich or deplete from the tank. This lets you know exactly how much you're putting it in and what concentrations. So mass, weight per gallon, or some substance per gallon, some sort of unit volume of fluid going into the tank. And then you've got some idea of what's going out. And this whole system, we're assuming, is going to be a steady state, meaning that the volume of the tank's not going to change. The flow rates are even. What's going in is going to equal to what's going out, as well as the substance is fully mixed. So you don't have salt settling to the bottom. You don't have some substance floating to the top. It's thoroughly mixed into the fluid. So keep in mind, you're concerned with how much of the particular chemical in question is flowing through this whole system. Okay, in this particular example, just to make it easier, we've got a problem. I didn't write it out into a word problem, so I just gave it to you as the flow rates. What you're going to know, a flow rate in and flow rate out is going to be 10 gallons per minute. You got a concentration going in, so you've got, say, a tank that you're feeding this from, and in that you've got 1 pound for every gallon of fluid going into the one pound of substance, in this case salt, going into the tank. And you've got a known tank of 100 gallons, so a volume of 100 gallons. So this is your given. You've also been given an initial value of 10 pounds of salt in the tank. Again, so just using this basic example, so you got a flow rate going into the tank, and they're flowing in a particular concentration of salt, of 1 pound of salt per gallon. You also know what's going out. It's a steady state, constant volume. You got a 10 gallons per minute going out. But here's the thing. The level of salt is constantly changing. Remember, you've got 10 pounds of salt in the system originally in a 100-gallon tank. That's only 0.1 pounds of salt per gallon. And you're putting in a concentration that is 10 times that. So this is going to, but it's a much bigger volume. So this tank is going to be in a constant changing state of salt coming out of the tank, especially since it's thoroughly mixed. And the amount of salt that's actually in the tank, you could just look at that as changing with respect to time. So it's a derivative of the salt. All right, so that's how we're going to set the problems up. You can go back to this particular slide. This is on Blackboard, and you can look and see how the problem actually gets set up. You're really trying to find the rate that the salt is changing. And I'm saying I can't emphasize that enough. I could give you this in terms of percentage, like if you're mixing a concentration into a CNC tank. I can give it to you in metric. I can give it to you in English. But the point that you're trying to do is trying to find how much salt you're moving through this system. Now, let's look at some of these numbers that I've started off with. You got a model. You need a model to know the concentration of the tank at any given time t. So if we look at this and turn it into a differential equation, what's going into this tank, what's going out of this tank can just be is a derivative. All right, the rate of change with respect to time, the salt's changing with respect to time. That ultimately is how much salt you're putting in versus how much salt is coming out. So you're looking at how much salt is, how the rate of salt is actually changing inside the tank. You know, and it's just the difference between what's going in and going out. And that is your differential equation. I mean, it's not written mathematically, or not quite mathematically, but this is what you're looking at. The real question is defining these two terms. You know, how do you set these up mathematically, or set these up in a mathematical way? So the concentration rate is just whatever the concentration is, you know, in this case 1 pound per gallon, times the flow rate, and that puts it in respect to time. This lets us know how fast the salt's going in and out. And keep in mind that the concentration rate going out is constantly changing. So you don't know that. So that's going to have to be done in terms of a function. So breaking it down a little bit, you got a concentration rate going in, which you know, a flow rate going in, which you also know, minus a concentration rate going out, which you don't know, and a flow rate going out, which you do know. Using the variables that we've been provided, you end up with the rate of change of salt at any time t is equal to the concentration of salt going in times its flow rate minus this constantly changing amount of salt going in or coming out times its flow rate. And that's our differential equation. All right, that's how we set the problem up. All right, so now I'm going to go through a quick little kind of run through, let you see, you know, kind of write this thing out so you have a list of how to handle this. First, you want to establish the rate that's being added to the system. So you're looking at what's going in, you know, for your differential equation. So that's concentration times the flow rate. Then you want to figure out the function for what's leaving. It's a function because this is a constantly changing variable. All right, so what's going out, you know, times the flow rate going out. Next, you can start to establish your differential equation. You know, and all it is just, you know, your rate of change of the salt in the tank is the flow rate going in minus the flow rate going out. Then you got to put it into standard form of a differential equation. You know, when I say a standard form of a differential equation, what I mean is, you know, is it going to be a first order linear differential equation, a separable and autonomous Bernoulli equation, some different types of differential equations that you're going to need in order to start finding your solution and in essence build your model. So solve the differential equation. Now when you solve a differential equation, you end up with a general solution. So now you have your initial value, what's going on at tank t or time t, and that gives you a particular solution, and that defines your mathematical model. Your particular solution in this case is a mathematical model. So let's go through our example. All right. At t equals 0, a tank contains 1 kilogram of salt dissolved in 100 liters of water. If salty water containing 1 kilogram or 1/4 kilogram per liter of salt enters at a rate of 3 liters per minute, and the solution is draining from the tank at a rate of 3 liters per minute, predict how much salt will be in the tank at time t. You know, and let A of t equal the amount of salt at any time. So we're just telling us that the variable of A is going to be representative of salt. So that's the problem. So let's start looking at what we know here. I got some things highlighted in red. So at t equals 0, so we're looking at the initial value here, times 0. So before the spigots come on, a tank contains 1 kilogram of salt. All right, so that's our initial value. We got an amount of salt in that tank at time 0. And it's dissolved in 100 liters of water. So now we've got a volume of the tank. So we got a volume, and this volume is, since it's steady state, 3 liters per minute, 3 liters per minute in and out. That's going to be constant throughout the problem. So we got 100 liters of water in that tank. Now our concentration is 1/4 kilogram per liter. Okay, so that is the amount of salt that we're putting into that tank. You know, significantly more significantly more than what we have going into the, or actually into the tank. All right, so we got a concentration going in, and we're trying to figure out how much is in the tank at any time t. All right, so that gives us enough information that we can actually solve this problem, and we can create a mathematical model to answer the question. We're trying to predict how much salt is in the tank at any time t, which is really what that question is, or that statement is: predict the amount of salt at any time t. Now, when solving a problem like this, one thing you want to do, and any problem for that matter, any engineering problem, or probably most problems for that matter, is establish what you know. Establish what you know right away. Square it away, get it organized, and put it in a place where you can actually reference it. So what do we know? We know the flow rate in and out is 3 liters per minute. We know that concentration going in is 1/4 of a kilogram, or 0.25 kilograms per liter. So right now we know the rate in. We know the volume is 100 liters, and we got an initial value. So this is all of our given. We're good to go. We know this information. Now we can start, looking at our differential equation, set everything up, plug it in, and go through a solution. So our differential equation, remember, I'm letting A equal salt. Is the variable for salt. So dA dt, the rate of change of salt with respect to time in the tank, so what's going on in the tank, is equal to the rate that the salt enters minus the rate that the salt leaves. All right, so it makes sense. So when we look at this equation, we can plug things in. What's the rate that the salt leaves? Well, it's the concentration of the salt, which is 1/4 of a kilogram per liter, and the flow rate is 3 liters per minute. Cancel out liters, we end up with kilograms per minute of salt going into the tank. We know there's 3/4, because 3 times 1/4, 3/4 per kilogram every minute is going into that tank. So we can see it's almost as much salt started into there. Not quite, but every minute we're building up on that. Now, what's going out? What's the rate that's leaving? We have a variable of what's going out, because we know that's changing because we're constantly putting something in. And it's flowing out at 3 liters per minute, and it's over 100 liters of water. So again, liters come out, and we end up with a flow rate, the amount of salt going in versus the amount of salt going out, or in this case, a constantly changing rate of salt going out. So we simplify it a little bit, go through the math. The liters drop out. So we end up with dA dt is equal to 3/4 per minute, kilogram per minute, is equal to 3 over 100 minutes times the change of salt, or salt at a given salt at t of t. Now we go from here and we put it into the standard form of a differential equation. And just from looking at this differential equation, it should be apparent to see that this is a first order linear differential equation. So if we just add the rate of the salt leaving to both sides, and I got rid of the units, we end up with the first order linear differential equation in the standard form. So dA dt plus 3 over 100 times A of t is equal to 3/4. That's the rate going out, or rate going in. Rate going out, rate going in, what's going on in the tank. Standard form of a linear differential equation is just dy dx plus p of x times y is equal to f of x. You got the derivative of y with respect to x and the variable of y. Here we have the derivative of salt with respect to time and the variable of salt. Here we have p of x, just the coefficient, is 3 over 100, which is p of x, and then it comes to f of x, which is just 3/4. So we have it in the standard form of a linear differential equation. So that means now we have to, define our p of x, in this case p of a, since we changed the variable for salt, and our integrating factor, and go through our solution. So p of a we know is 3 over 100, and our integrating factor is just e raised to the integral of 3 over 100 dt just solving for an integrating factor for a first order linear differential equation. Go through the integration of that, and that's just e raised to the 3t over 100. The 3 over 100 is a constant. The antiderivative is just time, just the variable of time. So now we have an integrating factor. For integrating factor, we go and take the integrating factor and multiply both sides of our first order linear differential equation. So that's what we're doing here. Our integrating factor times dA dt plus 3 over 100 at is equal to 3/4 times the integrating factor. Now, remember, when using first order linear differential equations, the integrating factor just turns this into the product rule, and we end up with the integrating factor times a of t as a derivative is equal to the 3/4 times the integrating factor. So this is just reversing the product rule like we've done in the past with first order linear differential equations. So we have a derivative is in the equation times 3/4 of e raised to the 3t over 100. So now to solve that, we just integrate both sides, or take the antiderivative. So now we're taking antiderivative of both sides. So keep this in mind. You're taking the antiderivative of a derivative. That's going to leave us with the argument. And on this side, you've got a constant of 3/4, and you've got basically one of the laws of taking the antiderivative of an x, or a base e, is going to be 100 over 3 times e raised to the 3t over 100, plus your constant of integration. And that's what we got here. The antiderivative of a derivative is just the argument. It's equal to 3/4, which was just the constant, times 100 over 3 times e raised to the 3t over 100 plus the constant of integration. And you see our 3's are going to cancel out, and then 100 over 4 is just 25. And then we also divide by our integrating factor from both sides. And what this step does is it puts solves our equation explicitly in terms of how much salt, or the rate that the salt is actually changing. Okay, so what does it get? It eliminates the integrating factor from this side of the equation. It cancels the integrating factor off of this coefficient of 25, and now you end up with the integrating factor times the constant of integration. And that is your general solution. So we've got a general solution now. So we know the salt at any time t is equal to 25 plus the constant of integration times e raised to the negative 3t over 100, since we divided by the integrating factor. Now remember, we got an initial value. At time t, the level of salt in the tank is 100 kilograms. So at time t, the level of salt in the tank, time t equals 0, is 1 kilogram. So we got an initial value we can plug in. T equals 0. All that's going to do is make this value of 1, and we're going to equalize that to 1 kilogram. So you have 1 kilogram is equal to 25 plus c times e raised to the negative 3 times 0 over 100. That gives you a constant of integration of negative 24. And you can plug that back into the general solution, and you get a particular solution. In this case, it's the mathematical model that we were looking for. So we know the salt at any given time t is equal to 25 minus 24e raised to the negative 3t over 100. And, supposedly, as time goes on, we can start putting in different times, as this process, this system's running, and see how the rate or the amount of salt changes. So what I did was I went ahead and decided to do that. So I got the model here for the system, and I put it into an Excel file, our Excel spreadsheet, and I just said, okay, at time 0, we got 1 kilogram of salt per this model. I'm plugging 0 into the model, and that's what we end up with. But as time goes on, I looked at it in increments of 2 minutes. We can see that salt going in at 3/4 of a kilogram every minute is really increasing this amount. It's not going up by exactly 0.3, 375 kilograms, but it's going up pretty fast. And the rate of salt in the system does come up pretty dramatically. And just to graph it out to see it, in a more graphical term, more visual, this is what you end up with. So what I wanted you to get from this video was how to actually set the problem up. You go through the problem as it's written in text, so as it's written out in plain text, and you start looking for things that you You start looking for the information they tell you. You look for some sort of an initial value. So they're going to tell you something that happened at the beginning before the spigots come on. You want to look and try to identify the volume of water in the tank. You want to keep in mind what the flow rates are going in and going out, as well as what the concentration is going into the tank. Once you have all that information, you should be able to set up your differential equation, and from there you can solve it and come up with a mathematical model. I hope this was helpful. Again, this is Professor Cummings.